Hi guys, today's topic is error, how you measure error, what kinds of error there are, so the taxonomy of error, and just an abstract overview of the whole concept of error. Then we'll be able to apply it in particular cases of calculation later. Okay, so to start off with, x, the variable x, represents some quantity that you're trying to calculate, and x sub t is the true value of that quantity, the theoretical true value, and x sub a is the approximate value, right? So the value that the computer has recorded for that variable. The absolute error is the difference between the true value and the approximate value, right? So x sub t minus x sub a. Notice, by the way, it is the true value minus the approximate value, right? So you have to add the error in to the approximate value to get the true value, right? The error is the amount that you have to add to the approximate value to get the true value. The relative error is the ratio of the absolute error to the true value of the variable, right? The true value of the quantity you're trying to calculate. And it's denoted by rel, right? So that's the relative error, and error is the absolute error. And by the way, I will sometimes suppress the subscript a in here, right? Because basically, if we're talking about the error, the a here kind of goes without saying, but there are situations where we might want to clarify that. Let's see, here's some useful relations among these quantities. So for example, you can rewrite the relative error by replacing the absolute error by x sub t minus x sub a, and then splitting this up into two fractions. X sub t over x sub t is 1, and x sub a over x sub t. So the relative error can be thought of as 1 minus x sub a over x sub t. If you denote the relative error by epsilon here, then you can also rewrite this. You can also rewrite this expression. Well, let's see. If this is epsilon, then you can solve for x sub a in this equation, and you get that x sub a is equal to 1 minus epsilon times x sub t. Okay, so 1 minus epsilon is the ratio of x sub a over x sub t. Okay, so just to take a simple example, how about pi? That's something that, it's a transcendental number. It's not even an algebraic number. It's certainly a non-repeating decimal. So we never have an exact value of pi in a computer. Suppose we just approximate pi with 2 decimal places, right, 3.14. Then the absolute error is the difference between pi and its approximation, right? So that would be these remaining decimal places. Pi is 3.14159265535. I was never a pi freak myself, so I don't have more than about 5 digits of pi usually. And then the relative error would be this absolute error divided by the true value of pi, and this works out to let's see, 0.0005. So this is like 0.05%. That's pretty good, I guess, right? 2 decimal places. That gives you an error, a relative error of 0.05%. Right? So 2 decimal places is probably good enough for everyday purposes. Another example, let's look at that notorious example we considered earlier where we had the problem with representing 1/10 in binary, right, in the machine. So in binary, or the scientific notation, right, we can write it as 2 to the minus 4th times 1.1001 repeat in base 2, right? So that's the value we came up with by carrying out long division in binary numbers, right? And so in the computer, remember we represent it by its power. Oops. So we do have the power here, right? Oops, I did it again. And then we are able to represent 52 decimal places of the significand, right? So this is how the number is represented in the computer as 2 to the minus 4th times 1.1001, and then you carry out 52 decimal places here. So the absolute error would be what's left over when you subtract. So actually that's going to be 2 to the minus 4th times what's left over when you take the repeating decimal and subtract off this truncated version of it, right? So what would be left would be just the decimal part from the 53rd position on. So 2 to the negative 4th times 2 to the negative 53, that's where I got the 2 to the negative 57. And then this remaining decimal starts with the 1, and then it goes 0, 0, 1, 1, and then repeats afterwards. It's approximately 19 over 2 to the 61. It always feels a little weird when you're doing an error calculation and then you have to approximate the error calculation, but that's normal actually in this field. The error calculation, of course, itself, it's not of importance in itself. What is important is the actual value, and you want to know the magnitude of the error. But having an approximate error is usually good enough for our purposes. If you calculate the relative error, that would be the absolute error that we just got here divided by 0.1, or multiplied by 10, and if you simplify this expression you can get it down to this. Notice that the relative error in this case is a little higher than the absolute error because the true value was 0.1, and when you divide by 0.1 you multiply by 10. Relative error is a nice, precise way of measuring error, and it's well behaved under multiplication and division, as we'll see, and under operations by differentiable functions. However, it's not always immediately apparent what the relative error is in a number you're working with, and sometimes it's easier to work with a less precise concept, but a more perspicuous concept, a more visually obvious concept, which is that of significant digits, right? So significant digits, loosely speaking, roughly, they're the number of digits in your answer that are correct, right? Actually, we're going to give a more precise definition for significant digits. But loosely speaking, that's the idea. It's the number of digits in your answer that are correct. And by the way, when I say the number of digits, I mean the number of non-zero digits, right? So we start counting significant digits at the first non-zero digit. Not at the decimal place, but at the first non-zero digit. So consider, for example, the value of pi again, 3.14159265359 ... We could approximate that to 2 decimal places. We could just take 3.14. That's a very popular approximation in high school, right? It's good enough for everyday purposes, certainly, for carpentry and even most engineering purposes. I think it's adequate. We want to say, it looks like we could say, in this case, that approximation, 3.14, is accurate to 3 significant digits, right? 3, 1, and 4, they're all accurate digits in the base 10 representation of pi. And that is actually true. But the technical definition for being accurate to 3 digits goes like this. We say, what is the unit of value in the position of the third digit? So the third digit in this is 4, right? The 4 is in the hundreds place, right? It's in the second decimal place that represents hundreds, right? So the unit of value in this position, we could say, is this. It's 10 to the negative 2. That's our unit of value in the third digit. To be accurate to 3 significant digits, we want to say that the absolute error is less than 1/2 that unit. Right? So in a sense, we're saying that if we were to round it off to this unit, this is the value we would get. But in fact, we're giving a very precise numerical definition here. And so we're going to say that it's significant to 3 decimal places if the error in XA which in this case would be, let's see, 159,265, etc., right? So this would be the absolute error, is less than 1/2 of that unit for the third digit, which is the second decimal place. So in this case, u is 10 to the negative 2. This would be 0.005. So in general, we will say that a number or an approximation x sub a is accurate to m digits, or equivalently we'll say it has m significant digits, if the absolute error in this approximation is less than or equal to 0.5 times the unit value of that mth digit. Right? So u is the unit value of the mth digit. So because we're working in base 10, this is going to be some power of 10, right? U is always going to be some power of 10. Okay? So one thing we might try is, why don't we add the next decimal place into pi? So we could take 3.141, right? We could try that. Because 1 is, in fact, the next decimal digit. In base 10, it's the next digit in the representation of pi. It's tempting to say now that this is accurate to 4 significant digits, but actually that's not true, or at least not according to our precise definition over here, because it doesn't satisfy this inequality. In fact, the error in this, 3.141, would be this, 59265, so it would be 0.000599265. And because it starts off with a 59, it is not less than or equal to 1/2 the value of the unit in the fourth digit position, right? So in fact, this is still only accurate to 3 digits, not to 4. Okay, now, if you're not confused enough, let me try harder. Let's add another digit, but now we'll add an incorrect digit. If we wanted to add a 5th digit, the correct digit to add would be 5. You might argue that maybe it would be better to round it off to a 6, but I'm not going to add either a 5 or a 6. I'm going to add a 2, right? So this is clearly a wrong digit that I'm adding. So I'm going to take pi to be approximated by 3.1412, right? Now, it's certainly not accurate to 5 significant digits, right? However, this is a sufficient correction that this value is now accurate to 4 significant digits. Okay, we didn't add the correct value in the 5th digit, but we did increase the value of pi slightly, and we increased it just enough so that it is now accurate to 4 digits, at least according to this definition over here. So again, let's consider what the unit value is in the 4th position. By the way, I'm not saying it's accurate to 5 digits. I'm not saying it's accurate to this digit. I'm just saying it's accurate to this digit, the 1 there. This is in the 3rd decimal place, so the unit is 10 to the negative 3rd, or 0.001, right? And now the absolute error, the absolute value of the absolute error, is a difference between the true value of pi and 3.1412. So if you subtract that, what you come up with is 0.00039. Now that is in fact less than or equal to 0.5 times this u, which would just be 0.0005. So this approximation, 3.1412, does satisfy the definition for having 4 significant digits. It's accurate to 4 digits. It is not accurate to 5 digits, right? So we're not saying that the 2, specifically we're not saying the 2 is accurate, but this is considered accurate to 4 significant digits. When you're doing a long calculation, or even a moderately long calculation, a calculation of several steps, you may find that at one step, you suddenly, your answer suffers a dramatic loss of significant digits. And this phenomenon is called loss of significance errors. That's a slightly ambiguous term. Loss of significance could mean even a small, even losing 1 significant digit. But in fact, this term is usually used when there's like a dramatic drop in the number of significant digits. So as an example, suppose you want to calculate square root of 101, right? Well, okay, so you can do that. I've done this here to 6 significant digits, right? 10.0499. That's accurate to 6 significant digits. Now, suppose I do a multi-step calculation, though, where I want to take the square root of 101 minus 10. Right? So I'm taking the square root, and then as a second operation, I'm going to perform the subtraction. Now, my first step was accurate to 6 significant digits. But when I subtract the 10, I get this value, right? That this 10 cancels, and I get an approximate value of 0.499. Now, the problem is this is only accurate to 3 significant digits, right? In fact, I've only got three digits here, right? I only recorded 3 digits. So this could not possibly be accurate to more than 3 significant digits. So this is a case where just performing one simple operation, a subtraction in this case, reduced our accuracy from 6 significant digits to 3 significant digits, right? And this is the kind of thing that can happen with addition and subtraction. Not so much with multiplication and division, but it's a particular danger with addition and subtraction. So we could say, in this case, if you were working with a function f of x equals radical x squared plus 1 minus x, and you wanted to plug in 10, then you would be evaluating this expression, right? And you may think that, well, your square root function works well, it's accurate to m significant digits. However, this only slightly more complicated function, radical x squared plus 1 minus x, suddenly has a dramatic loss of significant digits, right? In this case, it had only half as many, well, for that particular value, when you plugged in x equals 10, it had only half as many significant digits in the final answer. Now, let me try to convince you that this kind of problem actually does not arise with multiplication and division. So let's consider multiplication, and we'll analyze the relative error in multiplication. Now, I'm going to be a little loose with here. I call this a back-of-the-envelope calculation. I'm not trying to be totally rigorous here, but recall the formula that we saw earlier, that the approximate value of x is equal to 1 minus epsilon times the true value of x, and recall that epsilon is the relative error, right? So if epsilon is the relative error, then we have this formula, right? And in fact, you can think of this as characterizing the relative error. If this formula holds, then epsilon is actually the relative error. Okay. Now let's apply this formula to the case where we multiply 2 numbers together. So suppose we want to multiply x times y. Well, that's basically, if you're doing this, for example, on a calculator, and incidentally, that's a good way to think about this. You could think about doing these calculations maybe on your phone calculator or something that has a limited number of decimal places or significant digits. Maybe you've only got 8 significant digits on your phone calculator, right? And then you could think about how the error accumulates over the course of multiple calculations. That's a good way to think about it. So in this case, suppose we want to multiply 2 numbers together. Now, we may already have done some calculations to come up with values for x and y. So x and y themselves are represented by approximations on your calculator, right? You have approximate values for x and y. And therefore, when you want to multiply them, you're going to be multiplying their approximate values, right? So the answer you get is going to be approximately the product of the 2 approximate values, right? Now, I'm going to use this formula and substitute it in for both x sub a and x sub y, and y sub a. So x sub a is equal to 1 minus epsilon sub x, this is the relative error in x, times the true value of x. And y sub a, the approximate value of y, is 1 minus epsilon sub y, the relative error in y, times the true value of y. If you multiply this expression out, you get the true value of x and the true value of y. I combine those at the end here, xt times yt. If you multiply these 2 expressions, 1 minus epsilon x times 1 minus epsilon y, you'd actually get 4 terms. You get 1 minus epsilon x minus epsilon y plus epsilon x times epsilon y. I have left out the epsilon x times epsilon y because normally that would be very small. It would be much smaller than these other terms. So I said we can just approximate this expression by saying it's 1 minus epsilon x plus epsilon y all times xt times yt. Now if you look at this, what do we have here? We've got the approximate value of xy is approximately equal to 1 minus epsilon x plus epsilon y times the true value of x times y, right? And so if you compare that to this, what you can see is that the epsilon here corresponds to epsilon x plus epsilon y in this expression, right? Therefore, we can summarize this by saying that the relative error in multiplying x times y is approximately the relative error in x plus the relative error in y. Okay, so the relative error in the product of x and y is approximately the sum of the two individual relative errors. Now that's interesting and important because it says that when you do multiplication, the relative error only increases slowly, actually, right? You just add the two relative errors from the previous answers. And that is not going to cause any dramatic loss of significance, right? If you add two relative errors together, at worst, this might be twice as big as the bigger of the two relative errors. So you might lose only 1 digit in significance, right, when you do that. If you double the relative error, that would amount to losing like maybe at worst, one digit in significance. But on the other hand, when you're doing addition and subtraction, there is actually no limit to the number of significant digits that can be lost. So we saw here we lost 3 significant digits because the two numbers we were subtracting shared the first 3 digits. They were identical in both of them. When they canceled, then we only had 3 significant digits left. So with addition and subtraction, there's no limit to the possible loss of significance. On the other hand, with multiplication and also division, because division is just multiplication by a reciprocal, they're pretty well behaved. Generally are only going to lose at worst 1 significant digit in a multiplication or division. Let's do a case study on numerical evaluation of the exponential function. This is in the textbook, Atkinson and Hahn, page 50. Recall from calculus the power series development of the exponential function. E to the x equals 1 plus x squared over 2 factorial plus x cubed over 3 factorial, etc. Right? So this seems like it's a nice way to actually evaluate the exponential function. Now suppose we try to evaluate e to the negative 5 using this power series. And again, imagine you're doing this on your phone calculator and it only has 8 digits. Right? So you've got an 8-digit calculator and you're trying to work out the value of e to the negative 5 using this power series from calculus. Okay, so you plug in negative 5 for x and you get 1 minus 5 plus 25 over 2 minus 125 over 6 plus 625 over 24 minus, etc. Now, let's suppose you have lots of patience. You may be willing to plug in 10 or 20 or 30 terms or however long it takes to get a good approximation. By the way, you may remember from calculus that when you have an alternating series where the terms decrease in absolute value, then you can actually get an estimate for the error by just looking at the last term. So you can carry this out as long as you want until you get it sufficiently accurate. Except that there's a problem. You might think that it's simply a matter of doing it for as many terms as necessary, but there is a more fundamental problem here. If you look at the values of these terms, let's see, 1 minus 5 plus 12.5 minus 20 point something plus 26 point something minus, etc. You notice that these terms are rather large. E to the negative 5, as it turns out, has an approximate value of 0.0067, so it's a small number. Whereas these numbers that come up in the power series are comparatively large. They're like 10,000 times larger or 100,000 times larger, right? Now, the problem is that if your calculator is only accurate to 8 digits, that means, let's see, we got 1, 2, 3, 4, 5, 6, 7, 8. So we got these 8 digits here, but that means that the error in this value may be as large as 0.5 times 10 to the minus 6, right? So the 8th digit here is in the 6th decimal place, so that represents a unit of 10 to the minus 6th, and we multiply by 0.5. So the error could be as large as this. So already in the 4th and 5th term here in the series, we've already introduced errors as large as 0.5 times 10 to the negative 6. Now, you can't get rid of an error once it's been introduced. I mean, you might get lucky. You might introduce a compensating error, an error that goes in the opposite direction, but there's no guarantee that that will happen. So the best we can say is, the error in the complete sum, when we add up all the terms of the series, all 20 or 30 of them, however many we're going to do, there's no reason to think that the error won't be as great as 0.5 times 10 to the minus 6th. Now, given that the true value is only about 0.0067, this error of 10 to the negative 0.5 times 10 to the negative 6 would represent only 4 significant digits. Okay, so putting this all together, what we're saying is that if you work out however many terms you want of the power series here, and you're working on a calculator that has 8 digits of accuracy, nevertheless, your final answer is only going to be accurate to, at best, 4 significant digits. Okay? So just because your calculator has 8 significant digits doesn't mean that your result is going to be accurate to 8 significant digits. And again, it's because of these dramatic loss of significance errors that we run into, right? Because we have these large numbers that are canceling in the final answer, and we're losing, 4 digits of accuracy, right? We have a calculator that has 8 significant digits, but we lost 4 of them in the course of doing this sum, right? So the moral here is that if you're adding up a bunch of terms, adding or subtracting a bunch of terms, and the individual terms are significantly larger than their sum, then you can expect a large loss of significance, right? A large loss of significant digits in your answer. Okay, so 2 other important types of error are underflow and overflow. So these are things that can happen in the course of a calculation that will throw the calculation completely off the rails. Underflow is when in the course of a calculation the computer encounters a number that's too small, too close to 0 to be represented as a number that's different from 0, and then the computer simply replaces it with 0. And of course, that can have catastrophic consequences if you replace a number by 0. Like suppose you want to divide by it, then that's going to cause all sorts of problems. Or suppose you want to multiply it, it's going to make everything 0 when you multiply it. Overflow is the opposite sort of problem. It's when in the course of a calculation a number becomes too big, either positively or negatively, to be represented by a numerical value in the computer, and then the computer just replaces it by plus or minus infinity. I can give an example of both of these using the same function. So we'll look at the function f of xy. It's a function of 2 variables. So f of xy equals the 10th root of x to the 10th plus y to the 10th. Okay? So to get an underflow error, consider what happens if you try plugging in 2 to the negative 110th power for x, and the same thing for y, 2 to the negative 110th power for y. So if you do that, you plug in those values for y, then x to the 10th becomes 2 to the negative 1100, and y also becomes 2 to the negative 1100. Now, these numbers are too small to be represented on the computer. Remember that on the computer, we saw earlier, the smallest positive number that can be represented on the computer is 2 to the negative 1074. These numbers, 2 to the negative 1100, cannot be represented on the computer, And so when MATLAB comes to this point in the calculation, it will see simply 0 plus 0, right, inside the radical. And then it'll take the 10th root of 0 plus 0, and it'll say the final answer is 0. Now, it's easy enough to work out symbolically what the true answer is. When you multiply these two together, it's like multiplying, when I add these two together, it's like multiplying by 2. So 2 times 2 to the negative 1100 would be 2 to the negative 1099, and then the 10th root means you divide the power by 10. So it's easy enough to work out on paper the exact answer, right? The correct answer is 2 to the negative 109.9. Notice that the correct answer is actually within MATLAB's capacity to represent. This is a number that could easily be represented by MATLAB. So when you're doing a calculation like this, it can be quite frustrating. You give it an input and ask it to evaluate a function, and you know that it's capable of representing the correct answer, and it can be a little mystifying at first why MATLAB produced the obviously wrong answer of 0, right, when it seems like it's fully capable of representing the correct answer. And the problem came because during an intermediate step in the calculation, an underflow occurred, right? At an intermediate step, the numbers were too small to represent, and they were replaced by zeros, and that screwed up the entire subsequent calculation. So the answer was completely wrong. In a similar way, you can get an overflow error, right? So if I just plug in x equals 2 to the positive 110 and y equals 2 to the positive 110, then we get a similar overflow error. Now when you plug those in, raise x and y to the 10th power, we get 2 to the 1100, positive 1100 power, and plus 2 to the positive 1100 power. Now also recall that the greatest number you can store in MATLAB are on the order of 2 to the 1023rd, right? If you get up to numbers on the order of 2 to the 1024th, they're all considered infinity by MATLAB. So when MATLAB sees these two numbers, it has no choice but to represent them as infinity. And then it sees, well, we seem to be taking the 10th root of infinity plus infinity, and that would be infinity. And so it'll give you the answer of infinity. Once again, it's easy enough to calculate symbolically the correct value. Again, if you add these two numbers together, they're the same number, so it's like multiplying it by 2. This would be equivalent to the 10th root of 2 to the 1101. Divide the power by 10, and the correct answer would be 2 to the 110.1. Once again, this answer here, the correct answer, is well within MATLAB's capacity to represent numbers. And so it might be a little mystifying when you plug this problem into MATLAB that it gives you such an obviously wrong answer when it seems capable of giving you the right answer. And again, the problem is because at an intermediate step in the calculation, an overflow occurred. We had numbers that were bigger than MATLAB's capacity to represent them, and that screwed up all subsequent calculations of the problem. And we ended up with a completely wrong answer at the end. Now, sometimes there are workarounds for these loss of significance errors, and also for the overflow and underflow errors. Workarounds sometimes consist in simply rewriting the function in a different form so that the problematic aspects don't arise. For example, consider that function we looked at earlier when we had the loss of significance error. F of x equals square root of x squared plus 1 minus x, and we looked at the case when x was 10, right? And we saw that trying to evaluate f of 10 causes a big loss of significance error. Well, the source of that error was that we were subtracting two numbers that were very similar in size, right? And therefore a lot of the leading digits canceled, and we lost significant digits because of that. To avoid that problem, what we can do is we can rewrite this expression so that it involves addition instead of subtraction. So what we do is we use the difference of squares rules, right? Think of this, radical x squared plus 1 minus x as a fraction over 1, and we multiplied by a kind of conjugate expression, radical x squared plus 1 plus x, over the same thing. And now the difference of squares rule says when we multiply a minus x times a plus x, we get a squared minus b squared, or a squared minus x squared. Anyway, this is going to be x squared plus 1 minus x squared. The x squareds will cancel, and the numerator becomes simply 1. In the denominator, we get x squared, radical x squared plus 1 plus x, right? So now we have an equivalent function, but it doesn't involve subtraction, it involves addition. So now, when we plug in 10, we'll be adding square root of 101 plus 10, and we no longer get the cancellation that caused a loss of significance. So when we add these two numbers up, we get 20.0499, and there's no loss of significance here, and therefore when we divide, 1 divided by 20.0499, remember when you divide or multiply, you generally do not suffer those loss of significance errors, so we maintain accuracy to 6 significant digits. So we can expect that this answer here, 0.0498756, would be accurate to about 6 digits. In the case of the exponential function, we were trying to evaluate e to the negative 5. So we can do a similar trick where we replace the subtraction by all addition operations. So instead of plugging negative 5 into the power series, we'll use the fact that e to the negative 5 is 1 over e to the positive 5. And we can evaluate e to the positive 5 without doing any subtraction. And again, subtraction was the problem, because when we were subtracting alternate terms, there were a lot of cancellations, and the sum ended up being much smaller than the individual terms in the series. But with e to the positive 5, that problem does not arise. We're adding up all the terms, and the sum will actually be larger than all the individual terms in the series. So we do not expect to get the same loss of significance error. Okay, so the terms are all the same, right? The individual terms have the same value. It's just that now we're adding them all instead of subtracting alternate ones. Now, I actually use MATLAB to simulate adding 21 terms of this power series, each term to 8 significant digits. There's a round function in MATLAB that you can use for this kind of thing, so you can tell it to round a number to a certain number of significant digits, or different options that it takes to round numbers. So anyway, I use that to add up the first 21 terms of the power series, but only to 8 significant digits, right? Normally, MATLAB would, of course, add them to to that 64-bit accuracy, right? But I intentionally made it less accurate, and it came up with a value for e to the 5th of 148.41315, right? So this is what you would get if you were adding all those terms up with 8 significant digits accuracy. Now, because I added a bunch of terms, and there's some slight inaccuracy in each one of the terms, this may not be accurate to 8 significant digits, but it should be close, right? In fact, I think it turned out it was accurate to about 7 significant digits. And then when you take the inverse of this to calculate e to the minus 5, or in other words, you're doing division, 1 divided by 148.41315, you would expect no significant loss in digits, right? So in fact, when you do this, you get 0.0067379474, and this turned out it was accurate. If you compare this with the exact answer, it's accurate to 7 significant digits. Let's see, in the case of the underflow and overflow example, we can come up with a similar workaround. We take the original function, the 10th root of x to the 10th plus y to the 10th, and we factor out an x. We factor an x out from inside the radical. So if you do that, you're left with just x on the outside, it's x to the 10th root of x to the 10th, which is just x on the outside. Inside, you have 1 plus y over x, all raised to the 10th power. The point of doing this is that now when we plug in x and y values that are of similar size, right, comparable size, y over x will be a reasonable number, right? It'll be close to 1, right? If y and x are close to equal, then this number will be close to 1. It won't cause any overflow or underflow. And because the x outside is not raised to a high power, that means we can even plug in large values for x without causing an overflow, and we can plug in very small values of x without causing an underflow, right? So let's see what happens when we plug in 2 to the negative 110 for both x and y. Then in the alternate expression, right, the alternate form of the function, we have 2 to the negative 110 outside. Now remember, this 2 to the negative 110, that's well within MATLAB's ability to represent, right, internally, so that doesn't cause any problem. Inside, we have the 10th root of 1 plus 1 to the 10th power, because now y over x is just 1, right? We plugged in the same value. That's no problem. That's just the 10th root of 2. So that's 2 to the 1/10th power. So you have 2 to the negative 110 times the 10th root of 2. And MATLAB should now be able to give you the correct value for this. Again, it's something that MATLAB is capable of representing. And with this formulation, it's also capable of computing it. There's no step that causes an underflow, right, if you define the function this way. Similarly, if you try plugging in 2 to the positive 110 for both x and y, again, you got 2 to the positive 110 out front. That's not too big for MATLAB to represent. That's easy to represent as a 64-bit floating point number. Inside, once again, we have the same expression. It's the 10th root of 1 plus 1 to the 10th. So now we have 2 to the positive 110 times the 10th root of 2, and MATLAB will be able to give you the correct answer, 2 to the 110.1, without causing an overflow, right? Now, by reformulating the function this way, we eliminated those two problems, but we actually introduced another potential problem. If you now try to plug in a very small value of x and a very large value of y, you will get an underflow, right? Because if x is very small, an overflow. If x is very small and y is very large, then y divided by x will be a very large number. In particular, if you try to plug in 2 to the negative 110 for x and 2 to the positive 110 for y, then y over x is going to be 2 to the 220, then you raise that to the 10th power. So this is going to be too big, and it'll cause an overflow. So MATLAB will be reduced to giving you the answer of infinity for this, right? So you can see that although this workaround works for some input values, it doesn't work for all input values. And therefore, you can imagine that you might actually have to do something rather complicated, where you have to actually have different definitions according to the x and y values, right? That might be the only way to comprehensively deal with a situation like this. One other important distinction to make in different types of error is that when you're doing a multi-step calculation, you have error that's introduced at each step, and you also have error that was introduced at previous steps that is propagated to the later steps. So propagated error is an important type of error to consider. So as I said, the idea is that propagated error is the error that was caused by earlier steps of the calculation, and we want to distinguish this from the error that is introduced anew when you're doing the current calculation. Okay, so let me do an example. Suppose you want to calculate the square root of the log of 2. So this is a two-step process. First we'll calculate log 2, and then we'll take the square root. And suppose we want to do the calculation with 6 significant digits, right? So imagine again you're on your phone calculator, and it only has 6 significant digits. So step 1, we're trying to calculate the value of log 2. The true value is whatever log 2 is. The approximate value to 6 significant digits is 0.693147. Okay, so that's what your calculator gives you. Now there's an error at this step. You take the true value minus the approximation to get the error at this step. Okay. Now this is not actually the propagated error. The propagated error is going to be the error at the second step that is caused by this error at the first step. Okay, so let's go on to the second step and see what happens. Now we calculate the square root of the approximation we got for the first step, right? So at the first step we came up with this value of 0.693147, which itself was only an approximation. Now we take the square root of that. If you take that square root to 6 significant digits, you get this. And so we can suppose this is what your calculator would give you for the answer. In fact, the calculator has now introduced a new error, a brand new error at this step of the calculation, because the actual square root of 0.69437 is not exactly equal to 0.83255. In fact, there's an error at this step, which would be the exact value of the square root of 0.693147 minus the value the calculator gives you, and there would be an error there. So this is the new error that's been introduced at the square root step. On the other hand, the propagated error is the error that we would have had to live with even if the calculator had calculated the square root exactly. So the propagated error is the error that would have arisen because of the difference between the true value of the square root of log 2 and the true value of the square root of the approximate value of log 2. So in other words, the propagated error is this. It's the true value of the answer minus the true value of the function applied to the approximated value from the previous step. Right? So we take the true value of the square root of log 2 minus the true value of the square root of the approximation of log 2, and this is the propagated error. So this is the error at step 2 that was caused by the error at step 1 over here. It's not equal to the error at step 1, but it's the error that was caused by the error at step 1. Right? So this is the propagated error. So you can think of it as, in this way, you can think of it, if x is the value you got as the result of the previous step in the calculation, then the propagated error is the exact value of, and I should say, and now at the next step we want to apply f. We want to apply some function f to the value we got at the previous step, right? Then the propagated error is the true value of f applied to the true value at the previous step minus the true value of f applied to the approximate value we actually got from the previous step of the calculation. So this represents the error that we would have gotten even if we were able to perform the current step of the calculation exactly. Right? Even if we were able to evaluate f exactly, we still would have gotten an error because of the inaccuracy in x sub a, right, from the previous step. Notice that when you combine the propagated error and the new error, this orange error and the green error, you get the actual error in the calculation. So the exact value of square root of log 2 minus the value that this 6-digit calculation gave us, this is the actual error, and it's equal to the sum of these two errors. So it's the new error, which was actually negative, plus the propagated error, which was positive, so they kind of canceled each other out. We actually ended up with a somewhat smaller error in our answer. So suppose you're doing a multi-step calculation, and we want to analyze one particular step where we apply a differentiable function f to the result of the previous step of the calculation, right? So x will be the value, the result of the previous steps of the calculation, and f of x is the value we want to calculate at this step, right? Well, we can use concepts from calculus to simplify the calculation or the estimate of the propagated error. Recall from calculus that if you know the derivative of the function at a particular point x naught, and you want to estimate the value of f at a nearby point x, right? You can do so because you know that the change in f of x minus f of x0 is approximately the derivative times delta x, the change in x, right? That's a fundamental identity in calculus. So we can apply that to this situation. We'll say that the propagated error, which is the propagated error in the calculation we're going to make at this step is, well, what the true value would be minus the value we would get if we could compute the function f exactly, but by applying it to the approximation we got from the previous step, right? So it's the true value, f applied to the true value minus f applied to the approximate value. That's the propagated error. And now applying this formula from calculus says that this is going to be approximately equal to f prime, at the approximate value of x times delta x, which is the true value minus the approximated value. Now this quantity, of course, this difference is exactly the error in x, right? It's the error in x from the previous step. So we can say that the propagated error at this step is going to be equal to f prime times the error from the previous step, right? So that's a nice, simple way to calculate propagated error. Another useful way to think of it is to rewrite this so we get an expression for the relative error. If you take this equation and just divide everything through by f of xt, right? Just divide the whole equation through by f of xt, you get this. And now on the left-hand side, you see we've got an expression for relative error, right? It's the true error divided by the true value, right? Or the absolute error divided by the true value. And we could think of that right-hand side as representing the propagated relative error. On the right-hand side, we've got f prime of xa over f of xt. Now I'm going to do something dubious here. I'm going to say, look, for practical purposes, xa and xt are pretty close together. And if f is not a badly behaved function, then f prime of xa should be pretty close to f prime of xt. So for most purposes, these two numbers will be close enough together that we can replace one with the other and still have a decent approximation, right? And so if you do that, you get this formula that says that the propagated relative error is approximately equal to f prime divided by f at the point xt, the true value of x, times the error in x. All right, so that's a nice formula for the relative propagated error. Incidentally, this quantity f prime divided by f is known as the relative rate of change, right? The derivative divided by the original function is the relative rate of change. You can also get it by taking the derivative of the logarithm of f, so it's also called the logarithmic derivative. But you can think of it as the relative rate of change in x. It's how fast f is changing in proportion to the value of f. And so what we can say is that the relative propagated error is approximately equal to the relative rate of change in f times the error in x. Okay? So with these formulas, it makes it relatively easy, if you're working with a differentiable function, to track the propagated error. And if you track the propagated error and also the new error at each step of the process, then you can do a full error analysis, right, of the whole computation. Of course, the new error at this stage of, or this step of the process becomes or contributes to the propagated error at the following steps of the process, right? So at each step, you have to track both of them. They both contribute to the propagated error at the ensuing steps. And by keeping track of both of them, you can do a complete error analysis of the entire calculation.